Hello, I am Flash Isaac. This is Flashlearners. You are now watching More Than 20 Days to Jamb, a series containing 120 episodes which covers all the topics in Jamb syllabus. Each episode comprises detailed class, questions, and homework. The questions and homework are from the Flashlearners Jamb application. This makes the app a requirement for this class. Visit Google Play Store or flashlearners.com to get the app. Do you have trust issue? Reach me on any of my social handles for activation guide or enquiries. Ladies and gentlemen, it is time to tell. Hey, this is episode number 20 of the 120 Days to Jamb Physics with Flash Isaac. In this episode, we shall be introducing a very interesting topic. Although many physics students find this topic very difficult, but I am here for you to show you that equilibrium of forces is one of the simplest topic you can come across in physics. In fact, in this series, I shall make all the topics in physics very simple for you. This is episode number 20. If you followed from episode 1 to 19, you agree with me that it has been very wonderful. How is this class going to be? In this episode, I shall introduce the concept of equilibrium of forces and explain the things you need to know under equilibrium of forces. In the next 3 episodes, we shall be solving questions or answering questions under equilibrium of forces. As we answer questions, the things I am not able to tell you in this episode, I will tell you in the 3 other episodes. The good news is that by the time we finish equilibrium of forces, no stone shall be left unturned. Equilibrium of forces. Equilibrium of forces. Now, what are forces and what is the origin of force? To understand forces and equilibrium of forces, you need to know more about motion. We've done much under motion. Now look at it. Motion is change in position of a body or of an object with time. Change in position. Change in position. Now, why do objects change position? What causes change in position? A great scientist, Isaac Newton, observed in his first law that an object at rest will continue to be at rest. If this object is in motion, it will continue in that state of motion in uniform straight line unless it is acted upon by a force, which means objects move as a result of force, which makes forces agents that change the state of rest of a body or uniform motion. Forces actually do 3 things. When objects are at rest, forces cause this object to move. When objects are in motion, forces can support the motion or stop the object from moving. Forces can make an object to change direction. When I say forces, you should not think of big things. If I am here, someone comes to push me, I fall this way. A force has been applied. Now, as you are running very fast or you are on top of Okada, the bike man is moving very fast. You will see air resistance. You see the breeze. Sometimes you'll be shedding tears. You see resistance from the air trying to push you back. The Okada is able to move because the air resistance is being overcome. So you see, even in fluid, which is air, there is opposition to motion. And from Newton's second law, he says that the rate of change of momentum of a body is proportional to the force applied. And from Newton's second law, we get the famous formula F is equals ma. Now remember, mass of an object is constant. Anywhere you take an object to the moon, anywhere, mass is constant because gravity doesn't affect mass. And when gravity acts on mass, it becomes weight. If mass is constant, from here, we can say that force is directly proportional to acceleration. This is Newton's second law. If force is proportional to acceleration, it means The more the force applied to a body, the more the acceleration. The less the acceleration, the less the force. So force affects the acceleration of a body. If that is clear, Newton's third law says that for every action, there is an equal and opposite reaction. Why am I able to stand like this? It is simply because the force that is acting downward, my weight, there is another force trying to balance my weight, and that force is equals my weight. Otherwise, I will fall down. If you look at that, it means for every object, you can take this object to be somebody, to be car, to be ball, whatever. If this object is here, there is a force pulling it down. You can draw the arrow like this, or you do like this. And this force is taken to be your weight. Weight will always act downward. So if this weight is acting downward, which is equals mg, so now the object is not falling, or whether it's falling, there is a force that is opposite the weight that is going up. So you can call this normal reaction or lift for aeroplanes, or reaction, N or arrow. That is reaction. The idea of reaction is, if I am pushing here like this, so long this board is not moving, there is another force that is against my force. So it's like something like this. So the one coming here, arrow like this, the one coming here, arrow like this. And look at it. Objects don't only go up and down. Objects can go forward or backward. If I apply a force here, okay, let me do it this way. If I either like this and I'm pushing this way, this is the same thing as something like this. It means you are pushing this way. So the arrow is what matters, not where you put it. This is the same thing as this. So if I have a force like this that is pushing this, let's call it this force thrust or applied force. If I apply force, if I'm pushing this here, there is a force that is against this motion that will want it not to move. For forces between two surfaces, friction is the force that opposes motion. If I'm pushing this thing like this and I'm doing like this, it is faster like this than like this. Why? The friction here is higher than here, because here the friction here is the air resistance, but here is a surface. And the rougher the surface, the more the friction. A surface can be so rough that you find it difficult to slide objects through them. Now let's call this force, let's say drag force or friction. The difference between drag and friction is that drag force occurs in fluid like water and air. So the force of frictional force or force against motion in fluids is the drag force. But for surfaces, it is friction. From here, we can see that basically 4 forces act on objects. Let's look at equilibrium. What is equilibrium? Equilibrium is a condition of an object where its state of motion or internal energy does not change with time. State of motion or internal energy does not stop with time, which means the net force is equal to 0. Take a look at this definition. Equilibrium of forces, or equilibrium, a body says to be in equilibrium if its state of motion or internal energy does not change with time. They did not say that if an object is in equilibrium if it is not moving. They did not say that an object is at equilibrium when it is moving. No. They say object is in equilibrium if its state of motion or internal energy does not change with time. Which means an object in motion can be in equilibrium, and an object standing still or in one place can be in equilibrium. That is also 2 types of equilibrium. We have the static and dynamic equilibrium. These are the 2 types of equilibrium. Before then, mechanical energy is the energy objects or bodies or humans possess either due to motion or due to position. If you are standing at a height, there is an energy you possess, and that energy is due to your height, potential energy. If you are moving, the energy you possess as a result of movement is your kinetic energy. Potential energy is mgh, the mass of a body times gravity times height, because we are talking about position. Height has to be there, and gravity acts on bodies at height. If you are moving, kinetic energy is half mv squared. Now, what is static equilibrium? Static equilibrium is simply equilibrium of a body at rest, or a body that is not in motion, which means the state of motion of the body is zero. The body is not moving and the internal energy is zero. So the equilibrium of an object or of a body that is not moving, that is referred to as static equilibrium. Now let's analyze. If this is an object, on what condition must this object be in static equilibrium, or what will make this object not to move? Since four forces are acting on the object, the lift or the reaction against your weight, which is taking it against weight, or the thrust pushing it this way, and the drag or friction pushing it back. If you have this, if the normal reaction is 20 Newton and the weight is 30 Newton, what will happen? The weight is pushing it down, and the normal reaction is trying to balance the weight. But since the weight is more than normal reaction, the object will go down. Now look at this. If the thrust, let's say the force here is 30 Newton, and the drag or friction is 20 Newton, you will see that the object will tend to move this way, because the force pushing it this way is more than the force taking it back. So if I'm here, okay, look at this. One person here, one person here. This is pushing this, taking this way. This is taking it this way. If the forces are equal like this, 30 Newton, 30 Newton, the object won't move. By the time this force is more than this, you see the object will be going this way. So this is what will happen. How about the situation where the weight is 30 Newton and the normal reaction is 30 Newton? You see that 30 in opposite direction, the net force or the available force will be 30 minus 30, that is 0 Newton. Now, in this case, the body is not going up, it's not going down. How about the situation where this becomes 30? You see that 30 Newton is dragging it this way or pushing it this way, another 30 is pushing it that way. The body will not move, right? So which means the net horizontal force is equal to 0 Newton. So a situation where the result, since all the forces are equal and opposite, or if they cancel out, we say that the result of all the forces, or the resultant force, or the algebraic force, or the net force acting on the system is 0. So that is the condition for equilibrium or for static equilibrium. The sum of the forces acting is 0. The net force is 0. That is what you see on your book, and you'll be surprised. How will forces be 0? So we have 30, 30, 60, 30, 120 Newton forces acting around. The resultant or the net force is 0 because opposite forces, they are the same. They therefore cancel out. Now let's see dynamic equilibrium. Now dynamic equilibrium is equilibrium of a body, or a balanced state of a body, a moving body with constant velocity. In your velocity time graph, you have something like this. A car starts from rest. Initial velocity is 0. Now the car accelerates. As it's accelerating, you see vroom. So it's accelerating, right? But the car gets to a point where it maintains that speed like this. As it's maintaining this speed, the velocity is constant. Velocity is displacement over time, which means change in displacement of a body with time is not changing. It is the same. The body is not accelerating. So a situation where the state of motion of the object is not changing. If it's going like this, it's going like that steadily. That is a dynamic equilibrium. The state of motion is not changing, and the velocity, there is velocity, it exists, but it is constant. Since velocity is constant, acceleration is 0 and there is no net force. if this is a car, you see that the weight always acts downward, right? And the normal reaction is against the weight. So since the normal reaction and the weight dey balance off, the net vertical force is 0. Now the applied force on the tire is taking the car forward this way, and there is air resistance that is stopping the car. Air resistance and friction. So all these forces are balanced because the velocity of the car is constant. If you didn't get anything I explained, know that for dynamic equilibrium, the car is not accelerating, because from here to here is acceleration, here is velocity. So for dynamic equilibrium, acceleration doesn't exist, it is 0. Acceleration will only exist in physics if velocity is changing, because acceleration is change in velocity. Moment is actually a force, the product of a force and its perpendicular distance. If this force is acting and the force times the perpendicular distance at 90 degrees, that is moment. If a force is inclined, moment is not force times the inclined distance or inclined force. You must resolve to perpendicular distance to solve questions under moment. We've done a lot in my resolution of vector classes. We shall do more. Calculations under equilibrium promises a lot of things, and it's an opportunity for you to improve on your resolution of vector skills. Just know that for moment of force is resolving forces. Now a couple is equal and parallel forces that are acting in opposite direction. Their line of action do not meet. Line of action is simply a place where the influence of forces reaches, or the point where the force is acting. That is line of action. And a good application of moment is door handle. As you see, you are applying the force on door like this, and towards a perpendicular distance. That is moment. And couple is the turning effect of forces. Some forces dey produce turning effect, like when you are opening a tap, you see that a force is producing turning effect. That is torque. Then looking at bodies can be rigid, bodies can be parallel, bodies can be non-parallel. And we resolve vectors. Resolution of vectors is bringing out vectors into its various components, because some objects are inclined. We take them to vertical and to the horizontal. We take them to vertical and to the horizontal, resolving forces in 2 dimensions. The resultant of vectors is one force that will give you the same effect as the other ones acting. And equilibrant in vectors, or equilibrium of forces, is actually a single force that tries to balance every other force coming. And center of gravity of any object is the point where the resultant weight of the object acts. If I give you something like this, a big ball, and here there are granites, concrete here, but here nothing, you will notice that the weight of the body or of the object is here, the resultant weight is here. So if you push this object, it will hardly move, because the center of gravity, or the where the resultant weight lies, is very low. By the time you fill it up to this point, you see that the resultant weight, or the major weight, will be around here. So the lower the center of gravity of objects, the more stable they are. That's why you see sport cars are not high, they are usually stable, so their center of gravity is low. So irrespective of how fast they move, they maintain stability. While buses or long trucks, if they move very fast, because of their height and the position of the center of gravity is high, they will be shaking, they will be so unstable. Short people, when they are running, they are stable on the ground more than tall people running, because tall persons, where their weight lies is higher than short people. Short people, they are summarized and sorry their resultant weight is low. That is stability. And talking about, since center of gravity is the point where resultant weight of object at, and it determines the stability of objects, we have 3 types of stability, or we have 3 ways to describe objects: stable, unstable, or neutral. Look at this. If this is a shape like this, and you put a ball here, if you push it slightly, you notice that it will return to its position. So when an object returns to its position after being displaced in lithium, that object is very stable. they push you, you come back. Even pendulum, you put it there, it comes back. There's a restoring force trying to put it back to position. And another example of stable equilibrium is a cone resting on its base. This is a cone. You see that it is resting on its base like this. Why? If you displace, if you push it a little, it goes up, it will still come down. It is stable. Unstable equilibrium is when you displace an object slightly, then the center of gravity changes entirely and it moves, it doesn't come back. Look at something like this, a heel or a tip like this. You put a ball like this, my guy, once you touch this ball, it's rolling, it's going up and down. So this is an unstable equilibrium. Now this is a cone lying on its tip, is in unstable equilibrium. This cone now, you manage to put it like this, something like this. You manage to stand it and it stands. By the time you touch it a little, it has gone. It is unstable. Now, neutral equilibrium is when you have a flat surface like this, you put an object, let's say a ball or a cone, lying on its side. If you push this ball, it rolls a little like this. But this here is the position or the center of gravity. As it's rolling, the center of gravity remains. It doesn't go up or come down. This object is in neutral equilibrium. Or a cone lying on its side. As you push it, the center of gravity remains. It rolls. That is neutral equilibrium. Now you hear of rigid bodies. Rigid bodies are bodies that don't deform, or objects that don't deform. There are some objects that when you apply a little force, it will scatter or it will break. In that case, that object is not rigid. A good example of rigid body is human being. Our body is rigid. It hardly scatters or deforms when force is applied. And parallel force are force that acts on the same or opposite direction in a plane. If you are given one plane like this and you see force is acting, so these ones, they are acting in the same position, these ones, they are acting in opposite direction, but the three forces, they are acting on the same plane. If I am staying like this force is also parallel in the sense that it's on the same plane. Okay, if I'm like this and persons are pushing me down or they are pushing me like this, that is force. So we represent them with arrow. If I'm pushing this like this, to represent it in physics, you draw an arrow with the head going here to show that somebody is pushing. So it can be human being, it can be machine. That is the use of arrows. The non-parallel forces are forces that don't intersect or form common plane. In parallel, every force is they're acting on a particular object. Different forces acting, this one here, on one object. But not parallel. Like you see, this is like a building. 20 Newton is pulling here, 20 is going here, 22. Different forces are acting. They are not on the same plane. They are acting on different planes. It means the forces are non-parallel forces. So we can have coplanar forces. If you have parallel coplanar forces, okay, what I just explained is parallel coplanar forces. Parallel forces are forces acting on the same or opposite direction. Parallel. They don't meet. Their line of action is not meeting, but they are acting on a plane. Why coplanar forces? Coplanar, they are forces that are acting on the same plane. If you have this plane or one object and different forces are acting on that plane, they are coplanar. So this is an example of parallel coplanar force. That being said, we look at Lami's theorem. This is the concept of Lami's theorem. He said if you have three forces in equilibrium acting like this, one is going here, one is going here, the force is proportional to the sine angle of the other two forces. If you have C here, the force, this force C, is proportional to the sine of angle between A and B. And this is angle between A and B is C. So you see like this, like this. So over sine C or anything here. For this A, the force on this A is proportional to the angle between the other two forces. So since we are dealing with A, it is proportional to the angle between C and B. That is sine of small a. This is equals. If we are dealing with this B, the force in this B, it is B over sine of the force between C and A, which is this force, like the force that is opposite it, or the force between the other two, B over sine B. So if you are given a question, you see 30 degrees here, and here you see B, you are asked to look for B. So long there are three forces in equilibrium, C over sine 30 degrees is equals A over sine A is equals B over sine B. Now, if you are given triangle of forces, they are simply forces acting in a triangle. You solve for the resultant. Then polygon of forces, they are forces of more than three sides acting, and there is no resultant. If you notice, these other parts of the class, I rushed them. Why? It makes more sense when you are dealing with calculation. Now, let's look at something. I've already explained this in diagram, in words, and so on. Now, direct questions actually come that require you to know this word for word or to understand this word for words. If you see a question and they say that which of the following is a condition for equilibrium of rigid bodies? Remember, rigid bodies are bodies that don't deform. Condition for equilibrium of rigid bodies under parallel forces. 1. Resultant force must be 0, which means the force acting here, everything has to balance. Sum of forces or moment must be equals 0. Moment is force times perpendicular distance. So the sum must be 0, meaning the ones acting this way are equals the one acting that way. Once you add them, they balance. The one acting this way is positive, the one acting this way is negative. So plus 20 Newton plus minus 20 Newton, that is 0. Sum of upward forces is equals sum of downward forces. Sum of clockwise forces equals sum of anti-clockwise forces. These are conditions for equilibrium of rigid bodies under parallel forces. For equilibrium of rigid bodies under non-parallel forces, 1. Line of action must meet at a point. The resultant should be 0. Algebraic sum of result forces in any perpendicular direction is respectively 0. And for equilibrium of 3 non-parallel coplanar forces, 1. Resultant of the two forces must be equal and opposite to the third. We are talking about something like this. Line of action must meet. All three forces must be concurrent. Concurrent means the three forces, they must meet at a point. They are not separate. They should meet at a point. And all algebraic sum of forces at a point must be equals 0. Ladies and gentlemen, this brings us to the end of this episode, which basically focuses on introduction to equilibrium of forces and explaining all the concepts you need to know. From the next episode, we shall be answering purely questions, and we touch things we are not able to touch if there is. So, I am begging, let me kneel down. Get the Flashlearners Jamb application. This is just episode 20. We still have 100 episodes to go. If you have the app and you do your assignments and you practice, the class will be easy for me and easy for you. Now, come to think of it. 1. What do you stand to lose installing the app and practicing? 2. Are you not the one writing the exam? Would you want to fail? So 3. What is your excuse? And 4. My contact is always there for you to ask me questions and make inquiries. So who much is given? If he or she likes, he can run away with it. Alright, see you in the next episode.